Okay, let's talk about chapter 13, which is solutions and colligative properties. Solutions, if you recall, are homogeneous mixtures of two or more substances. The thing doing the dissolving is the solvent. What's being dissolved is called the solute. You may have more than one solute. Well, let's go through some of the possibilities. Many of these can be homogeneous, but several of them have to be heterogeneous, and some of them are heterogeneous most of the time, to be realistic. So a lot of times we think of a solid dissolving into a liquid as a solution like salt water. You can dissolve a liquid into liquid like mixed drinks. Alcohol dissolved in the water is like your alcoholic beverages. A gas dissolved in a liquid like our carbonated beverages or soft drinks. Liquid into a solid, you can get some sort of amalgams, like your dental amalgams have mercury in it. It's a combination of metals, but the liquid is mercury. You can do a solid into a solid like in an alloy, but realistically those alloys were formed in the liquid phase and then poured into a cast and allowed to solidify. Gas to solid, that doesn't happen too often. A lot of times the gas just sticks to the surface of, say, a metal. Gas and a gas will mix with any other gas. A lot of times with solids and liquids or liquids and liquids, we worry a lot about solubility, but for gases and gases, since the intermolecular attractions are pretty low, any gas will mix with any other gas. The last two have to be heterogeneous, like a solid into a gas or a liquid into a gas. You're not going to get that to dissolve evenly, like dust and air for the solid, or your clouds or your fog for a liquid. If we're going to dissolve it, many times those heats of solvation are endothermic or exothermic. The delta H less than 0, then the dissolution tends to be favored. If it's positive, the dissolution is not favored. That doesn't mean it can't dissolve. There's a little bit more to it. A lot of salts are endothermic on solvation, but they do actually dissolve as long as it's not too endothermic. Now, another factor is the polarity of the solvent. Polar substances like to dissolve other polar substances. Nonpolar substances like to dissolve nonpolar substances. We call that the like dissolves like rule. For example, methanol has a polar group in that OH group, CH3OH, and it's very soluble in water because that OH group likes to hang out with water. Nonpolar groups tend to slide past one another. For example, carbon tetrachloride and benzene are immiscible or mixable because they're both nonpolar substances. We call that the general solubility rule. So that like dissolves like. Many ionic solids and your polar compounds will dissolve in a polar liquid like water. Pay attention to that salt solubility rules from chapter 4. Nonpolar things tend to dissolve in nonpolar things, as you might imagine. So based on that, which of these do you think would be soluble in water? Ethyl alcohol. Yes, that's soluble in water. Carbon tetrachloride, that's nonpolar as we just discussed, so no. Carbon dioxide only has slight solubility. So for the most part, no, unless you got it at high pressures. Ammonia, yes, it will dissolve. So let's talk about that solution process. A solution is saturated if it contains the maximum amount of solute it can at a particular temperature. Unsaturated just means it contains less than that amount. So it's not particular with the concentration. Supersaturated contain more than the maximum amount. You say, well, how is that possible? It just means that usually you formed it at a higher temperature where more would dissolve and allowed it to cool gently. A dilute solution just means you've got a little bit. A concentrated solution means you've got a lot dissolved. Sometimes we talk about certain solutions like ammonia or certain acids. Concentrated means it's the full strength solution. Usually it doesn't mean something specific, but it can in terms of certain solutions when it's the max concentration you can get commercially. Solubility of Ionic solids tends to increase with heating. Since most salts dissolve endothermically, most salts will improve their solubility by heating. If it's exothermic, something like calcium chloride is exothermic. Cooling it off sometimes might help, but a lot of times it's just heating it will do. You can see that from the graph. If you've got carbon dioxide, pressure changes have little effect on the solubility of liquids and solids, but if you're talking about a gas, you're going to be able to dissolve more in, like forming a carbonated beverage, dissolving it at pressure. You open it and goes psh, and it fizzes. That's because the pressure is being released and gas is escaping the solution. That's also why if you surface too quickly when you're scuba diving, you get the bends, because that blood plasma dissolves a lot more gas and it becomes trapped in plasma. If you release that pressure too quickly, it bubbles and fizzes out into your bloodstream, and that's what you call the bends. And that can be fatal if you're not careful. What you'd have to do is repressurize them in some sort of hyperbaric chamber and then redissolve the gases and then release the pressure more slowly. Is carbon dioxide more soluble in water at higher or lower pressure? At a higher pressure, gases are more soluble, so carbon dioxide would be soluble at a higher pressure. Colligative properties. Colligative properties are those properties that depend only on the number of particles dissolved in the solution. They don't depend on things like kinds of particles dissolved. Colligative properties are a physical property of the solutions. Things like vapor pressure, freezing point, boiling point, osmotic pressure. Vapor pressure is key to all those other properties. Boiling point elevation. If you're lowering the vapor pressure, then it's going to require a higher temperature to get the vapor pressure to equal the barometric pressure. So dissolving a solute into, say, water is going to make it boil at a higher temperature. The reverse happens with the freezing point. If I put salt on icy roads, I'm doing it so it forms ice at a lower temperature. So adding a solute will lower the freezing point, but will increase the boiling point. Amount of ionization. That also affects how much it's raised or lowered, for example, or how much the vapor pressure changes. A lot of times there's a property called the Van 't Hoff factor, given the variable I, and it tells you how many particles it forms. If it forms more particles, since the property is totally based on the number of particles in solution, more particles is going to be a bigger change for the same number of moles of solute dissolved, because you'll get more moles of particles. So sodium chloride ionizes to form 2 particles, and so I is 2. Calcium chloride ionizes to form 2 particles, so I is 2. Potassium sulfate forms 3 particles because you have 2 potassiums there, so I is equal to 3. If I take sucrose in a solvent water, I just get aqueous sucrose, so hey, I is 1 for all molecular compounds. So I get the biggest change in the boiling point for the potassium sulfate, since the I is the biggest, all other factors being equal. If you look at these next ones, sodium nitrate only forms 2 particles. Potassium chloride only forms 2 particles, as we mentioned before. Barium bromide, though, forms 3, because I got 1 barium and 2 bromides. So that looks like our winner, because sulfur dioxide is covalent and would only form 1 particle to the extent which it dissolves. So barium bromide forms 3 particles, and that would be your answer. Osmotic pressure is based on the particles dissolved as well. Osmosis refers to a solvent between 2 solutions separated by a semi-permeable membrane. The solvent passes from the lower concentration to the higher concentration. Examples, in terms of synthetic, would be cellophane or saran wrap. Biological ones can be your skin or cell membranes. Osmotic pressures can be large. A 1 molar sugar solution has an osmotic pressure of 22.4 atm or 330 psi. Since that's a large effect, you can use it to get molar masses of large molecules like your large polymers or biomolecules like proteins or ribonucleides or things like that. You can also purify water using reverse osmosis. That is, I get a pressure because the solvent wants to go from the less concentrated to the more concentrated in a effort to even out. That's why you don't drink salt water, because you disrupt that flow and you suck all the liquid out of your cells. But the liquid normally flows from less concentrated to more concentrated in terms of the solvent, in our case water. But if I supply the pressure and say in terms of a piston, and then I use semipermeable membrane, I can force the liquid to go the other way and purify water. They call that desalination. And for example, Fort Myers, Florida gets its water from the Gulf of Mexico using reverse osmosis. U.S. Navy submarines do that because you're not going to carry all that water when you're out 6 months at sea. Dialysis is a way of doing it, but it's more fancy than all that because you do want to allow certain solutes to pass to clean the waste products out from your bloodstream, not just remove excess water. Colloids are things that would not quite dissolve because the particles are too big. The particles don't settle out. They make the solution cloudy and opaque. Fog, smoke, paint, milk, mayonnaise, shaving cream, clouds, all examples. If they're hydrophilic means it loves water, and that means it's water soluble. Examples like that can include your biological proteins like blood plasma. Hydrophobic colloids dislike water and are insoluble. Hydrophobic colloids require an emulsifying agent to stabilize it. Homogenized milk is hydrophobic. You want to get that milk fat to dissolve in the bulk of the milk. Milk, therefore, is what they call an emulsion, where you use the protein casein as a stabilized agent to dissolve the butter, fat, and protein particles in the water. Mayonnaise is another example. Use vegetable oil and eggs in a suspension with water. The eggs use lectin from the yolk of the egg as the stabilizing agent, and that's a raw egg. Soaps are also excellent emulsifying agents. That's why Dawn takes grease out of your way. They're usually, traditionally, they've been sodium or potassium salts of long fatty chain acids, fatty acid chains. And what you would do is, historically, you'd use potash, which contains potassium, or sodium. You'd form lye soap by adding sodium salt or potassium salt. Usually by reacting a strong base, you separate the fatty acids from the triglycerides and then you can salt them out. Classic one is sodium stearate, formed from stearic acid. You got a long hydrocarbony tail that can interact with your grease, but you've got the polar head from the carboxylic acid, in our case, that can interact with the water. The result is a caging structure called a micelle, where the red heads refer to the water-soluble portion, and so they face out towards water, and the grease molecule would be in the center with the nonpolar chains. And that allows grease to dissolve. And say you clean your dishes. Hard water can mess that up. Iron, calcium, magnesium causes the soap fatty acids to precipitate. That's when you start getting soap scum and your shampoo doesn't foam up and you feel this icky scum that doesn't wash off. It's because those things are not water soluble and they don't come up. Chemically speaking, we can replace the carboxylic acid group with a sulfonate group or a sulfate group and form sodium. The top one is sodium lauryl sulfate, and that would be a lauryl sulfonate at the bottom. And you can easily see that they have a different group, but the same very concept long nonpolar molecule, but polar group at the end. These tend to be a little bit more soluble with hard water metal ions. But they're in common synthetic soaps. If you look at your shampoo bottle, it has sodium lauryl sulfate in it more than likely, and that is the actual soap.